Magnetic materials. Each electron in an atom has an orbital magnetic dipole moment and a spin magnetic dipole moment that combines vectorially. And the resultant for each atom combines with those for all the other atoms in a sample of a material. If the combination of all these magnetic dipole moments produces a magnetic field, then the material is magnetic. There are three general types of magnetism: diamagnetism, paramagnetism, and ferromagnetism. Diamagnetism is exhibited by all common materials, but is so feeble that it is masked if the materials also exhibits magnetism of either of the other two types. In diamagnetism, weak magnetic dipole moments directed opposite the external field are produced in the atom of the material when the material is placed in an external magnetic field, B external. The combination of all those induced dipole moment gives the material as a whole only a feeble net magnetic field. In a non-uniform field, diamagnetic material are repelled from the region of greater magnetic field. The dipole moment and thus the net field disappear when B external is removed. The term diamagnetic material usually refers to materials that exist only diamagnetism. 2. Paramagnetism is exhibited by materials containing transition elements, rare earth elements, and actinide elements. Each atom of such material has a prominent resultant magnetic dipole moment, but the moments are randomly oriented in the material, and the material as a whole lacks a net magnetic field. However, an external magnetic field, B external, can partially align the atomic magnetic dipole moment to give the material a net magnetic field. The alignment and thus its field disappear when B external is removed. In a non-uniform field, paramagnetic materials are attracted from the region of greater magnetic field. The term paramagnetic material usually refers to material that exhibits primarily paramagnetism. 3. Ferromagnetism is a property of iron, nickel, and certain other elements, and of compounds and alloys of these elements. Some of the electrons in these materials align their resulting magnetic dipole moment to produce regions with strong magnetic dipole moment. An external field, B external, can then align the magnetic moment of these regions, producing a strong magnetic field for the material as a whole. The field partially persists when B external is removed. In a non-uniform field, paramagnetic materials are attracted from the region of greater magnetic field. We usually use the term ferromagnetic material and even the commonly termed magnetic material to refer materials that exhibit primarily ferromagnetism. Diamagnetism. A diamagnetism material placed in the external magnetic field B external develops a feeble magnetic dipole moment directed opposite B external. If the field is non-uniform, the diamagnetic material is repelled from a region of the greater magnetic field towards a region of lesser field. We cannot yet discuss the quantum physical explanation of diamagnetism, but we can provide a classic explanation with the loop model. To account for the lack of magnetism in the absence of an external magnetic field, B external, we assume the atom lacks a net magnetic dipole moment. This implies that before B external is applied, as many electrons orbiting one way as orbited the other, with the result that the net upward magnetic dipole moment of the atom equals the net downward magnetic dipole moment. We turn on non-uniform B external. This large greater, this lesser greater. Okay. Then magnetic flux increase. So this is an electron, the atom, okay? And we have induced current makes downward from Faraday's law, okay? So that up, and then this means current is this one, electron goes this direction. This happens in all magnetic materials. The term diamagnetic material usually refers to materials that exhibit only diamagnetism, because many paramagnetism and ferromagnetism material, they also show diamagnetism. We know diamagnetism material put in a magnetic field, external magnetic field, it will produce a magnetic dipole moment, which is opposite direction of B. And in that case, the current in this way and the electrons go this way. We have analyzed above, and this circle of current will be exert a force, okay, IDL cross B, and the total F should be go upstairs. And in our case, this is our magnetic field. This is a greater magnetic field. This is a less greater magnetic field. Okay. Net downward magnetic dipole moment causes upward force. And in our case, is from greater magnetic field to lesser one. Paramagnetism. A paramagnetic material placed in an external magnetic field, B external, develops a magnetic dipole moment in the direction of B external. It's different, okay? This induced magnetic dipole moment is in the same direction as B. And in this case, current in this way, electron move in this way. If the field is non-uniform, the paramagnetic material is attracted towards a region of greater magnetic field from a region of less field. This is a great magnetic field, this is less field. And we calculate from above, it has force down. It's from the less to heavy, greater. In paramagnetic materials, the spin and orbital magnetic dipole moments of the electrons in each atom do not cancel, but add vectorially to give the atom a net and permanent magnetic dipole moment mu. In absence of an external magnetic field, these atomic dipole moments are randomly oriented, and the net magnetic dipole moment of the material is zero. However, if a sample of the material is placed in an external magnetic field, B external, the dipole moment tends to line up with the field, which gives the sample a net magnetic dipole moment. This alignment with the external field is opposite of what we saw with the diamagnetic materials.
We'll use these samples of bismuth and copper sulfate suspended from a light thread to show two types of magnetisms, paramagnetism and diamagnetism. Unlike ordinary ferromagnetism, which is a strong effect, para and diamagnetism are weak effects and exert small forces. When the poles of a large horseshoe magnet are placed around the bismuth is weakly repelled by the magnetic field. This is an example of diamagnetism. The copper sulfate is weakly attracted into the strongest part of the field, an example of paramagnetism.
A paramagnetic sample with N atoms could have a magnetic dipole moment with the magnitude of N mu if the alignment of its atomic dipole were complete. However, random collisions of atoms due to thermal agitation transfer energy among them, disrupting their alignment and thus reducing the sample's magnetic dipole moment. The importance of thermal agitation may be measured by comparison two energy. K bar larger than UB. What is K bar? K bar is 3/2 kT, the mean translational kinetic energy of an atom at temperature T. Remember that? And delta UP equal to 2 me.B external is the difference in energy between parallel and anti-parallel alignments, the potential energy change. We can express the extent to which a given paramagnetic sample is magnetized by finding the ratio of its magnetic dipole moment to its volume V. This vector quantity, the magnetic dipole moment per unit volume, is called magnetization M of the sample. Complete align of the atomic dipole moment called saturation of the samples. Saturation of the sample M, it should be a maximum because every atom aligned equal to total number N multiply the mu each for each atoms divided by volume. The unit M is the ampere square meter per cubic meter or ampere per meter. Magnetization curve N over M maximum. We look this experiment data. Okay, this data collect a different temperature, low temperature. Okay, very low temperature. Okay. This is called the Curie's law. This is a B external over temperature T measured in Kelvin. Okay, this is M over Mx. The Curie's law tells us that this M, equal to C constant B external over T. In other words, this is proportional, linear. Okay, and the C is constant. Okay. The law is actually an approximation that is valid only when the ratio B over T is not too larger. You see, only this part, this is linear, only this part satisfied. In this case, B external over T is less than 0.5. Okay. Or when the temperature goes low, B over T gets high, we have to explain with the quantum physics or magnetism. A paramagnetic gas at room temperature T 300 K is placed in an external uniform magnetic field of magnitude B 1.5 Tesla. The atoms of the gas have magnetic dipole moment mu 1.0 Bohr magnetron mu B. Calculate the mean translation kinetic energy of K of an atom of the gas and the energy difference delta UB between parallel alignment and anti-parallel alignment of atoms' magnetic dipole moment with the external field. We'll calculate this one first. Okay, This is the average energy of molecule. We put everything inside, okay, we get a small number, 6.2 times 10 to the minus 21 joule. Okay, it's about 0.039 electrovolt. And we calculate delta B equal to 2 mu dot B. We know mu, we know B, we get it easily, okay? Now, we compare these two. This one is much, much larger than this one. What does this mean? This means the thermal energy exchanges among the atoms during their collision, this one, can easily reorient a dipole. This very changes, okay? Ferromagnetism. A ferromagnetic material placed in an external magnetic field B external develops a strong magnetic dipole moment in the direction of B external. If the field is non-uniform, the ferromagnetic material is attracted towards a region of greater magnetic field from a region of lesser field. A ferromagnetic material has a strong permanent magnetism, but a diamagnetic or paramagnetic material has weak temporary magnetism. Iron, cobalt, nickel, gadolinium, dysprosium, and alloys of these and other elements exhibit ferromagnetism because of a quantum physical effect called exchange coupling. In this process, the spin of the electrons in one atom interacts with those of neighboring atoms. The result is an alignment of the magnetic dipole moment of the atoms, in spite of the randomizing tendency of the atomic collisions. This persistent alignment is what gives ferromagnetic materials their permanent magnetism. Of course, all this happens at below the Curie's temperature. If the temperature of a ferromagnetic material is raised above a certain critical value, called the Curie temperature, the exchange's coupling ceases to be effective. Most such material then becomes simply paramagnetic. That is, the dipoles still tend to align with an external field, but much more weakly, and the thermal agitation can now more easily disrupt the alignment. The Curie temperature for iron is 1043 Kelvin, about 770 degrees Celsius. This is Mr. and Mrs. Curie works in France together.
We'll use this Canadian nickel to demonstrate the effect of heating on magnetic materials. When the nickel is at room temperature, it is strongly attracted to a magnet. If we heat the nickel above its critical temperature, known as the Curie temperature, it loses its magnetic properties. When the nickel cools, it again becomes magnetic.
We'll use this piece of dysprosium metal to demonstrate the effects of changing temperatures on magnetic properties. If we cool the dysprosium to the temperature of liquid nitrogen and bring it near a magnet, it is strongly attracted to the magnet. When the dysprosium warms up, it loses its magnetic properties and falls away from the magnet. If the dysprosium is again cooled in the liquid nitrogen, it regains its magnetic properties.
These are regions of the crystal, throughout which the alignments of the atomic dipole moment is essentially perfect. For the crystal as a whole, however, the domains are so oriented. They largely cancel out with each other as far as the external magnetic effects are concerned. Actually, a piece of iron, as we ordinarily find it, is not a single crystal, but an assembly of many tiny crystals, randomly arranged. We call it a polycrystalline solid. Each tiny crystal, however, has its array of various oriented domains, just as in the above. If we magnetize such a specimen by replacing it in an external magnetic field of gradually increasing strength, we produce two effects. Together, they produce a magnetization curve of the shape shown in the figure. This is B0, this is Bm over Bm maximum. One effect is a growth in size of the domains that are oriented along the external field at the expense of those that are not. The second effect is a shift of the orientation of dipoles within the domain as a unit to become closer to the field direction. A ferromagnetic material placed in an external magnetic field, B external, develops a strong magnetic dipole moment in the direction of B external.
We'll use this coil wrapped around a soft iron core and a bar magnet to show the existence of magnetic domains. Any changes of magnetization of the iron inside the coil will send small currents through the coil, which will be amplified and fed into a speaker. When the bar magnet is brought up to the tube, a rustling sound is heard as the domains in the iron change orientation. This is called the Barkhausen effect.
These small compasses on pin bearings are models of the magnetic domains present in iron and other magnetic materials. Like real domains, these compasses can be oriented randomly, or they can be aligned by the presence of an external magnetic field. When a bar magnet is passed slowly over the model, the domains line up in the same direction. A rapidly changing magnetic field like the one from this oscillating bar magnet can randomize the domains.
Roland ring. This is Roland ring. Okay. You have a primary coil, the black dot, and a secondary coil, the orange dot. Okay. And you have a core. Current IP is sent through primary coil P, whose core is the ferromagnetic material to be studied. Here we used iron. And that is magnetized by the current. The extent of the magnetization of the core determines the total magnetic field B within coil. Field B can be measured by means of a secondary coil S. This is the B0 equal to mu0 n IP without the core. If we put the core, okay, then this we measure from S to B equal to B0 plus B material, which is much larger than B0. This is the curve, B maximum over M maximum. Okay, this is the B0 original magnetic field. Okay, Bm maximum is the maximum possible value of Bm, corresponding to saturation. A magnetization curve for the core material of the Roland ring is similar to the magnetization curve for the paramagnetic material. Now let's summarize. Diamagnetism, paramagnetism, ferromagnetism. When you put in external magnetic field, the induced magnetic dipole moment mu is parallel B and opposite direction. For this paramagnetism, they have induced magnetic dipole moment the parallel to B by the same direction. For ferromagnetism, they induce magnetic dipole moment parallel to B and in the same direction. Okay? They are the same. And this is very weak. This is a medium, and this is strong. And this diamagnetism material put in the external magnetic field, it will be repaired from greater magnetic field Bx. And they will be attracted by the greater magnetic field. And this is too attracted from great magnetic field B. Diamagnetic field is temporary. You withdraw the B external, it disappears. Paramagnetism is temporary. You withdraw the external B, it disappears. And ferromagnetism is permanent. You withdraw the external magnetic field, it still exists. And the difference between them, this is a strong, this medium is the temperature. When the temperature is high, the thermal energy is high, this is a paramagnetism. And when the temperature is low, and the heat education is low, and in this case, it's ferromagnetism. If the temperature go high, this one can become this one. Hysteresis. Magnetization curves for ferromagnetic materials do not retreat themselves as we increase and then decrease the external magnetic field B external. Look at this graph. We start from 0. This is external, B external. When we increase the B, the magnetic field of material goes up. But after reach the B, we reduce to be 0, it will not go to this way. It goes to this way. Okay, and then you go this way, come back. Okay, so the lack of retraceability shown in the figure is called hysteresis. And the curve BCDEB is called hysteresis loop. Note that at point C and point E, the iron core is magnetized, even though there's no current in the toilet winding. There's no external magnetic field. Okay. And this one is so important. This memory of magnetic materials is essential for the magnetic storage of information.
When an external magnetic field is applied to a piece of iron, there is a time lag before the iron becomes fully magnetized. We'll demonstrate that time lag using these two coils of wire on a U-shaped core. An alternating current at 60 Hz will be run through the first coil on the left. That current also drives the horizontal sweep of this oscilloscope back and forth at 60 Hz. The voltage induced in the second coil by the changing magnetic field of the first will be used to drive the vertical scan of the oscilloscope. The vertical and horizontal scans are initially in phase, and a straight line is displayed on the oscilloscope. If this piece of aluminum is placed between the ends of the two coils, there is no effect on the currents. If it is replaced with a piece of laminated soft iron, the second current lags behind the first, and the straight line becomes a loop. A piece of steel causes an even greater time lag between the two signals.